performance track. Right, so go ahead, guys.
Okay, so first of all, welcome. My name's Mark Ashdown. I am the EMEA team leader of the real world performance team, and we're part of database development. And I'm going to talk about cloud networking. Okay, safe harbor statement. If I start talking about any futures, which I shouldn't. So first of all, who are we? We're part of database development. We're a relatively small team. We've got members in HQ in Redwood Shores. We've got people on the East Coast and elsewhere in the US. We've also got a team in EMEA and over in China. If you add up our experience, we've got about 300 years of experience combined, which I guess is good in that we know the Oracle database. It's bad in that there's quite a lot of grey hair in our team. So what do? We aim to use the product, the Oracle database, as it was designed to be used, because that's how you get the best performance. So we try to use it as a relational database. And our remit is to help people, customers, both internal and external, to get the best performance out of the Oracle database. And what we try and do is we try and avoid guesswork. We apply data-driven techniques, so we have a look at the way the application is performing, get a holistic view of the application, so not only the database but the application as a whole, and then work out where performance can be gained, apply suggested changes, and then go back in until we get better performance. Our other remit is that we're here to share what we learn. So we share what we learn both internally within Oracle development, so we feed back issues to the development teams. We talk to the development teams with suggestions for improvement. We also talk to the apps development teams who are developing applications that access the Oracle database. And we also attend and present at occasions like this. And we run 3-4 day performance courses. There's fewer running these days because, of course, with lockdown, it makes attending courses a bit more difficult. So what we're going to talk about now is based on our experience and observations of applications being moved to the cloud. So what people ideally want to do is we've got an on-premise system with an application server and a database, and we want to lift it up and put it straight on the cloud, and performance will be the same, if not hopefully better. That is the aim. And what we're here to do is discuss reasons related to networking, why that might not always be the case. So firstly, a reality check. Quite a lot of applications exist in isolation these days. So if there's multiple components to a particular application, it is possible that not all those components will be moved into the cloud en masse. If they're not, then there may be integration points that have to be maintained, but those integration points remain within the on-premise systems or maybe in another cloud provider. Now, those integration points could be just sending of files periodically. But in these days of microservices and Kubernetes and all that sort of stuff, the incidence of near synchronous or synchronous integration points is becoming more and more frequent. And if you're moving to the cloud and you have local on-premise systems, a longer network hop will be introduced. That is just a fact, the law of physics. So where do we move it to? Ideally, what we do, if I'm a customer, we move it to one data center. So we have the application server and the database ideally next to each other in the same data center, which is hopefully what we have on premise. But sometimes what we see is people moving to two data centers for some reason. Maybe their application server is already in existence somewhere and they choose a different data center to run the database. So immediately we can see that there are potential issues of network latency between these two sites. Sometimes people talk about putting the database in the cloud and keeping their application servers on premise. So then the application servers will talk to the database over the internet. And again, we're going to have another network hop. So how long would the network hop take? It depends on distance. It's basically a function of the speed of light and the number of network devices you have to transfer over between the hops. So if you're doing international round trips, 6,000 miles, it's probably going to take 100 milliseconds. You can read this as well as I can. Regional, 600, 10 milliseconds. Metropolitan, within the same area, say of London, it's going to be 60 miles. If it's local, like I said previously, the application server next to the database server, then the propagation delay is going to be more a function of the number of network devices you have to go through. So, what is the impact of increased round trip time? From the application perspective, the database appears slower. Now, sometimes we have a problem talking to application developers because their concept of database time is I issue a call from my application server, I wait for the response back from the database, and the difference between those times is the database time. Now that, of course, not only includes the work on the database and the time within the database, but also the network round trip to the database. Now, from the database perspective, we have a situation that if my application acquires a connection and I'm doing a series of actions using that connection, the time that I grab that connection will be extended. And that means that any resources that I hold will be held on for longer. And if they are held on for longer, that means the chances of contention on that resource will be increased. So the example here is row level locks. If I take out a row level lock, I may hold on to it longer. And if on my on-premise system, I see a low level incidence of contention on row level locks, and then I move it to a cloud environment where the network hops are longer, there is a possibility that the incidence of row lock contention will be increased. So what can I do about it? Because an individual session will be able to do less SQL round trips per second with longer latency than I could do on premise. So the only way around that is to enable enough sessions to be able to maintain the same throughput. But of course, you have more sessions, which there are potential issues with more sessions. There is a potential, if you've got a problem with row level locking, that there is more sessions potentially grabbing those row level locks. And also, we've got more sessions running in the database. And it depends on how many sessions you've got, but the more sessions you have, the less efficient the operating system can be. So we have a potential impact on efficiency and scalability. So a quick diagram here about where my time goes. So an end user makes some sort of request, goes over the network to the application server. The application server does some processing, needs some data from the database, goes to the database returns back over the network to the application server. The application server then reformats, thinks it needs some information, and then goes back to the database server, comes back over the network. The application server then formats the reply back to the end user, and the end user gets a reply. So if we divide the components up, we can see that the gray, and a darker gray there for some reason, is network time, blue is application time, and the green is the database time. Now, if we move this application onto the cloud and the speed of CPUs and everything else is the same, it is likely that the time on the application server is going to be the same. It is likely that the time on the database server is going to be the same. So the only thing that will change is the network time. And that is the database time. So now what I'm going to do is show you a demo. I'm driving the demo from another machine, so that's why I occasionally will look over to my left. Right, so we've got a few monitor screens here. On the left, we've got, well, before we do that, what I'm going to do is go back to here and just explain. We've got a data center here from London to Frankfurt, which is 396 miles. We wanted to present that in terms of the US distances on the West Coast. So we thought that's got to be about San Francisco to Seattle. Shows that we have no concept of distances here in the UK and the US. And the actual distance is 680 miles. So the nearest equivalent that I could find was San Francisco to Eugene, which is 435 miles. So it's a fair distance away. And we're going to run a swing bench OLTP workload. We've got a database, we've got our application server in London. We've got our database in London. And then we've got another database in Frankfurt. So that's what we're going to run with. And here we've got stats from the London database. And here we've got stats from the Frankfurt database. And these are identically configured. They're ATP databases because those are easier to set up. We've got a few stats here. We've got a commit count. So this is the number of user commits. We've got the execute count, which is the number of SQL statements executed per second. And we've got the stat SQLnet round trips. And here we've got the number of connected sessions. And there we've got the same in Frankfurt. So what I'm going to do is I'm going to start the load in London. And I'm not trying to stress the system here. So we're running a relatively low load. We're running 10 sessions here. And you can see that we've got a response time of about 30 milliseconds, transactions a second of about 600. And if we look here, we've got, and you might not be able to read the numbers, so you'll have to trust me. We've got we've got a round trips of about 5,200 a second, depending on the time that we're looking at it. We've got an execute count of about the same. So it's about 5,200, 5,100. And we're running at a commit rate of about 860, 870. So the SQLnet round trips are the same as the execute count. Now, for those of you who've run Swingbench before, you probably haven't seen this, but what we're running here is the client-based SOE benchmark. So we don't use PL SQL here, we use SQL. So every bit of SQL is a round trip. So let's start another one in Frankfurt. Now I've started it behind the scenes here because I need to change some of the sections in a minute. Okay, so we can see here immediately that we've got 10 sessions and the commit count is about 91, 80, 85 a second. The execute count is about 540. And the SQLnet round trips are about 540, 560. So fortuitously, and I promise you we haven't fixed this, the Frankfurt data center is about 10 times slower than the London data center. And the reason is the application server that we're running Swingbench from is in the same availability domain as the autonomous TP database in London. And then we're going over the network to Frankfurt. So what can we do to make the two behave in a similar way insofar as the number of commits a second? Now, we can't change the latency of the network. The only thing we can do is increase our utilization of the bandwidth of the network. So how can we do that? We can do that by changing the configuration here and increasing the number of sessions to 100. And you can see immediately here that the commit count is now up to about the same in Frankfurt as it is in London. The execute count and everything are about the same. And the number of sessions we've increased from 10 up to 100. And you can see here that the response time in London is 33 milliseconds. In Frankfurt, it's about 10 times more. But the transactions a second are about the same. So in order to get the same throughput, we're not going to get the same response time, but in order to get the same throughput, we need to increase the number of sessions in proportion. Now, if you have a dynamic connection pool, what you'll probably see is the connections start floating up. But if you have a fixed number of connections, you will have to adjust to increase the number of connections. Does that make sense? And what I'll do now is I'll kill that one. And I'll run the same demo again, but using the stored procedures rather than the client-based. So you can see here immediately that even in London, the execute rate goes up to 22,000. The SQLnet round trips stay at around 3,250. Okay, so you can see here that each round trip involves more than one SQL execution. And that's what we would expect if we were using PL SQL, which we actually are at this time. So if you have an AWR report, for instance, and you compare the execute count to the SQLnet round trip, you can see whether there is likely to be any PL SQL calls in there. So let's see what the effect of running this in Frankfurt is. So again, it's exactly the same thing. And you can see we're running PL SQL transactions here. And you can see that the transactions a second here are about 262 as against 1,500. So it's roughly, we've increased the transaction rate in, we've doubled the transaction rate in Frankfurt. Because here we're 40, here the transaction rate is 264, and here it's about 1,600. So if we multiply that, divide that by that, we get about 5. So if we increase the number of connections by about 5, we should get equivalent performance. Now you may ask, why don't we get 10 times? The two applications are not the same. The client-based and the PL SQL-based application are not the same. So you just have to compare each one individually. Okay. So that's good. If we've got an OLTP application and we've got a different performance due to network latency, then we've got quite a straightforward way of solving it, which is to increase the number of connections. Increasing the number of connections has other consequences, so you just have to be careful of that. But what about this one? We've got the same thing here. We'll let it stabilize out. And we've got this. So we've just got one session running here. And that one session, we can see, is running at about 124 executes a second, about the same SQLnet round trips per second. So again, it looks like what we're doing is we're doing one SQL call per round trip, and we're doing about 23 commits a second. Transactions a second, 20. You can see that as well as I can. Okay, now this is typical, and this is what we see quite a lot of a batch routine. So it's a single-threaded batch routine, effectively. So now I'm going to start up the load in Frankfurt, and I start it because I've got space and I don't need to change it here. So this, again, and I'm not sure what happened here, but up to about 3 days ago when I last tried this, we did get the 10 times load, the 10 times of the response time at Frankfurt. For some reason, it seems to be shorter here, and I'm not sure why. I didn't have time to diagnose that. But we've got a single threaded application doing work against the database. And we can see that it's, in this case, 3 times slower, at least half as slow anyway. And previously, what we had, we had the option of just throwing more sessions. But this is a batch routine that's been developed and working for a long time. So what can we do? We can't throw more sessions at it because that would mean that we have more than one session doing the same sort of thing, and that may result in a lot of contention. So what we'd have to do if we were going to do that is we'd have to modify the application to actually use multiple sessions. I guess the other thing we could do is convert it to using something like PL SQL that runs on the database only. But this is the big potential problem that you have with cloud networking if you're running this on the application server into the database. Does that make sense? Well, nobody can answer because you're on mute. So that was a silly question. I apologize. Okay, so back to the presentation. And we'll skip through this. Batch workload. You can see it was 10 times. So there may be no simple solution to this. So if you're analyzing your application to see whether it would be compatible with a cloud-based deployment, and your application server to database latency is increasing, you have to be very careful about single thread or serialized components. So here's an example for you. And this is a real world example. Application was moved from an on-premise to cloud. We think nothing else was changed. So they didn't change the version of the application. It was a pre-built app. And we haven't changed the database version. We haven't changed the statistics, etc., 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 which is a whole new different presentation. So let's say everything was the same. The online performance was okay. The connection pool seemed to go up, and the throughput was okay. But the overnight batch, we have a problem with. Now we know, because we've investigated the application, that everything that runs on the database is initiated from the application servers. And we know that nothing is in PL SQL. So everything involves a SQL net. Every SQL involves a SQL net round trip. So if we have a look at the AWRs from 2 10-minute runs here, this is the on-premise. You can see here that we've got a database time of 0.6 per second. CPU of 0.5 per second. So we've got 0.1 seconds per second of weights of some description. Okay, so if we have a look at the cloud version of this, we've got less database time. We've got 0.2 seconds per second of database time. And our definition of database time is the amount of time foreground active sessions spend in the database. So it's from the database receiving a request and delivering a request back out. And we can see the database time is 0.2 seconds per second, and the CPU is 0.2 seconds per second. So there's no wait. So it's not waiting for anything. You ask your DBA, what's happening to my database? The database is slow. We say, well, it's not waiting for anything. And you can see that we're about, from the executes per second, we're about 4 times slower. And incidentally, we're slightly higher than that on the consumption of CPU. So there's no waits on cloud, so we can't do anything. If we have a look at the wait events on premise, we can see that 81.9% of the time is on CPU, which is good. 0.7 is on network, 0.3 is on some sort of concurrency. And we've got a little bit of SQLnet more data to client. If we have a look at the cloud version, we've got 80.5% of the database time on CPU. The second one is a control file sequential read, which usually says to me, nothing much is going on. And then we've got various network and other related waits. So it's not a bad situation on the cloud. And we've actually got less waits for more data to client, which is curious. So if you have a look at the AWR statistics, we can see that the SQLnet round trips from and to client per second are about 3,400. We can see that the SQLnet round trips to and from client for the cloud are about a quarter of that. Similarly, the bytes received by SQLnet from the client, we've got that magic quarter, and we've got that magic quarter of the bytes sent to the client. So we know that if we go back to upwards to the executes a second, we've got 2,000 executes a second, 538 executes a second. So we've got round trips per second here is 888 per second here is about 4 times more. And we've been told that there's no PL SQL, so this is the number of round trips, let's say approximating the number of SQL statements. So we can see that the SQL statements coming in are less. So we're not driving the database as hard in this case as we are in this case. So the only way we could improve that is to increase the number of sessions. And if we have a look at the SQL statistics, the executions, we can see that we've got 3 statements here. And the number of executions is about the same. And the rows per execution, that means the rows returned from each execution of the statement is 1. So we're executing this statement 106,000 times, and each time we're getting 1 row back. Now, if you were to modify your application to retrieve more than one row at a time, it would make it a lot more network efficient. But this is not what they've done here. It is curious that the first statement never retrieves any rows, which makes you wonder, I guess, why it was there in the first place. But I'm sure there was a good reason.
Hey, Mark, sorry to interrupt. You have 5 minutes here.
Yep.
We wrap this session. Yeah, go ahead.
Okay.
Thanks.
So estimating the impact. The workload. A little knowledge of the application goes a long, long way. If you're a database administrator, try not just to remain within your database space. Try and find out, maybe from the AWR, maybe from talking to people, exactly what is going on. You can get a lot from the AWR, and you can discover what the network performance is going to be. So you can find the increase in round trip time. You can use standard network tools, but don't use TNS ping because that just goes to the listener. So estimating the application perspective, the application does not see database time. Its concept of database time is the database time plus the network time. So we can use the basic agreement to estimate the increase in network time. So we've got the round trips from the AWR, and then we can times that by the increase in round trip time. We can then compare that to the database time and find out what the gap is. This is one of the problems scenarios. If we always update a control and not commit it, we're holding on to that lock too much. So where does my time go? Application time, database time. We move into the cloud, the network time. So whose problem is it? I guess one of the questions we have is, obviously it's a high important system. So who is it to blame? Is it the crusty old database administrator? He seems to be quite happy, so that's good. Is it the young and thrusting application server developer? Or is it a network engineer? Now, I don't know what a network engineer looks like, so I just found this. Or is it physics? Is it that you can't break the speed of light? Or, as Scotty would say, I cannot change the laws of physics, Captain. Which is strange, as he spent his career doing that. So thank you. I've got 7 minutes left. Well, 2 minutes, I think, because I had my session cut short. If we've got any questions, I'm around. We can open up the questions now. Otherwise, thank you very much. And it is